The 2026 Tesla Model 2 is shaping up to be the company's most disruptive vehicle yet, a compact electric car designed to bring long range, smart efficiency, and everyday practicality to the mass market at a price that finally makes Tesla ownership accessible to almost everyone. Rumors of this car have circulated for years, but now signs are pointing to its arrival sooner than many expected. Tesla's careers page has recently revealed dozens of new openings for delivery preparation specialists, a strong indication that the company is bracing for record-breaking deliveries in the upcoming quarters. This kind of large-scale preparation has historically coincided with the launch of major new products, and many observers believe that the momentum building within Tesla is aimed directly at the release of the long-awaited Model 2. What sets the Model 2 apart is its potential driving range, which is expected to stretch between 300 and 400 miles on a single charge, an extraordinary achievement for an EV priced in the affordable category. The secret lies in a fusion of groundbreaking technologies that are just beginning to mature. One of the most promising breakthroughs comes from structural battery composites, known as SBCs. These materials, highlighted by the World Economic Forum as one of the top 10 emerging technologies of 2025, allow carbon fiber to serve not only as a structural component but also as part of the energy storage system. Researchers at Chalmers University in Sweden have already demonstrated that SBCs can deliver an energy density of 30 watt-hours per kilogram while achieving stiffness levels of 76 gigapascals and maintaining efficiency over 1,000 charge cycles. Applied to a production car, these materials could reduce vehicle weight by around 10%, which in turn boosts range by as much as 70%. Alongside SBCs, advances in solid-state aluminum-ion batteries promise to make the Model 2 safer, longer-lasting, and more environmentally friendly than any EV in its price bracket. Unlike conventional lithium-ion packs, aluminum-ion batteries have been shown to retain over 99% of their capacity after 10,000 cycles. They resist extreme heat up to nearly 400 degrees Fahrenheit, withstand punctures without leaking or catching fire, and can be recycled thanks to aluminum fluoride frameworks. Together, structural battery composites and aluminum-ion cells could enable Tesla to create a car whose chassis is both body and battery, resulting in an exceptionally safe, lightweight, and efficient machine that offers far more range than most consumers expect from an affordable EV. The Model 2 is also expected to feature a low-power mode to limit energy loss when parked. Vampire drain has long been a nuisance for EV owners, but Tesla's solution reduces consumption dramatically by pausing non-essential systems such as cabin preconditioning, overheat protection, summon standby, and background tasks that usually wake the car. With this feature, energy loss can fall to just 0.4 to 0.6 kilowatt-hours per day, translating to a standby draw of only 17 to 25 watts. Without low power mode, the draw typically doubles or triples, meaning a parked car could lose as much as 7% of its charge over 3 days. By contrast, the Model 2 with low power mode will be able to sit idle for days or even weeks with minimal loss, provided Sentry mode is off when not needed. Another defining factor is the Model 2's aerodynamic profile. Tesla has already pushed boundaries with the Model 3's drag coefficient of 0.23, but the new compact EV may take that down to around 0.21. Paired with a slightly smaller body footprint of about 2.1 square meters frontal area, the car would require significantly less energy at highway speeds. At 70 miles per hour, consumption could drop from around 226 watt-hours per mile to about 207, nearly an 8% improvement. Design elements such as a smooth roofline, flush door handles, a flat underbody, subtle rear diffuser, and active grille shutters further reduce drag, while low rolling resistance tires contribute another 6% efficiency gain. Altogether, these changes could push the real-world highway range of a 60 kilowatt-hour Model 2 close to 330 miles. Urban driving conditions will extend this even further thanks to regenerative braking. By recovering 10 to 15% of energy normally lost in braking, the system effectively increases usable range by up to 50 miles per charge in stop-and-go city traffic. A 60 kilowatt-hour battery operating at an average consumption of 200 watt-hours per mile could return roughly 6 extra kilowatt-hours from braking energy alone, equivalent to an additional 30 miles. The combination of aerodynamic efficiency, structural weight reduction, low power standby, and regenerative braking is what makes the Model 2's 300 to 400 mile estimate not just plausible but practical. Durability and simplicity play equally important roles in the Model 2's design. Tesla is likely to adopt a hybrid body structure using both aluminum and high-strength steel. Aluminum reduces weight while resisting rust, while steel provides exceptional strength where it matters most, such as in the pillars and crash zones. This combination improves torsional rigidity, stability, and safety without adding unnecessary bulk. Crash structures are engineered to absorb and dissipate energy more effectively, reducing peak impact forces by up to a quarter compared to traditional designs. Meanwhile, adaptive LED headlights, consuming only a fraction of the power of halogen lamps, will deliver superior illumination and safety while extending usable range at night. Inside, Tesla continues its philosophy of minimalism. Instead of cluttered dashboards filled with buttons and switches, the Model 2 will rely on a single central touchscreen complemented by a powerful voice assistant and over-the-air updates. By reducing mechanical failure points and enabling faster software-based improvements, Tesla ensures long-term reliability while also minimizing maintenance. Voice control means that drivers can keep their eyes on the road more consistently, potentially reducing distraction time by as much as 30%. Materials chosen for the cabin will be both comfortable and durable, with synthetic leathers and anti-stain coatings able to withstand years of wear and remain easy to clean. Passenger comfort will not be sacrificed either, as the car's wheelbase and flat floor design allow for generous headroom, a convenient step in height, and ample cargo space expandable through split-folding seats. From a performance and cost of ownership perspective, the Model 2 is expected to outshine its competitors. Its permanent magnet synchronous motor eliminates rotor copper loss and consistently operates within the 94 to 97% efficiency range. Paired with a silicon carbide inverter that reduces switching losses by up to 10% compared to older systems, the Model 2 delivers both high efficiency and high torque density in a compact, lightweight package. Energy consumption is projected to fall in the range of 14 to 16 kilowatt-hours per 100 kilometers, compared to 17 to 19 kilowatt-hours for many budget EVs, saving the average driver hundreds of kilowatt-hours per year. A simple single-speed reduction gear transmission minimizes moving parts, which cuts down on maintenance and avoids costly failure points common in traditional vehicles. Regenerative braking further reduces wear on brake pads, extending their life by as much as 90% in urban conditions. Advanced driver assist technology is also expected to come standard. Tesla's latest vision hardware includes high dynamic range cameras and precision radar that allow for accurate detection of objects, lane markings, and speeds even in challenging weather. These systems support automatic emergency braking, lane keeping, and adaptive cruise control. Studies have shown that features like these can reduce rear-end collisions by up to 40%, adding to the Model 2's safety credentials while also improving energy efficiency through smoother driving patterns. The manufacturing process behind the Model 2 is as revolutionary as the car itself. Tesla's gigacasting approach, using massive presses to form the entire front and rear underbodies in single pieces, reduces parts count dramatically. Combined with a structural battery pack that doubles as the vehicle's floor, this method eliminates hundreds of components and meters of welding, lowering both costs and production time. Learning curve effects in battery manufacturing further drive prices down, with costs per kilowatt-hour expected to drop by 15 to 20% as production scales. These efficiencies are essential to reaching Tesla's ambitious target of offering the Model 2 at under $25,000, with some projections suggesting a price tag closer to $10,000 in certain regions as volume grows. When viewed together, these advancements paint a clear picture. The 2026 Tesla Model 2 is not just another addition to the company's lineup, it represents the culmination of years of innovation in batteries, manufacturing, design, and software. With a projected range of up to 400 miles, exceptionally low maintenance costs, a minimalist but practical interior, and a price point that finally brings Tesla into the realm of true mass-market affordability, the Model 2 could become the car that redefines electric mobility worldwide. For many buyers, the most important factor may be the price. For others, it will be the extended range or the drastically reduced cost of ownership. But taken as a whole, the Model 2 embodies Tesla's mission more than any car before it, to accelerate the world's transition to sustainable energy by making clean, advanced technology available to everyone.